This year generally, and June particularly, marked the 120th anniversary of Albert Einstein's so-called miracle year of 1905. It was in that year, between March and September, that he published four studies that would forever change the laws of physics and ultimately the conception of the reality of light, matter, time, and space. His first paper on June 9, 1905, was about photoelectric effect, titled A Heuristic View of the Production and Transformation of Light. In that paper, he introduced the astounding idea that light is composed of both energy and quantifiable particles, which he called quanta, or photons now. That alone would have guaranteed him a place of exalted honor in the world of physics. However, he followed that up with a second study in a physical phenomenon called Brownian motion, which showed that matter is composed of atoms. His third paper was considered the most promising. It was special relativity. It postulated that the speed of light is immutable, constant, and independent of the observer's motion. That meant, with the exception of the constant speed of light, everything is relative, including time, distance, and mass. As if these were not revolutionary enough, he published a fourth paper about the equivalence between matter and energy, condensing it into the most famous formula in history, E equals mc squared. To understand the incredible sweep of a 26-year-old's intellect, I spoke to Dr. Clifford Will, distinguished professor of physics at the University of Florida and the 2021 winner of the Einstein Prize of the American Physical Society, as well as the 2019 Albert Einstein Medal. With over 225 scientific articles, including 23 major review articles, 31 popular or semi-popular articles, and 4 books to his name, Professor Will is an authority on Einstein. The interview is a precursor to my eventual documentary on Einstein's miracle year, set for release in the next few weeks.
One, two,
Welcome to
three.
Einstein Report, Professor Will. It's a great pleasure to have you.
Thank you. Thank you. Great to be here.
Like I mentioned in my email, this is for a documentary that I'm working on the 120th anniversary of the so-called miracle year of 1905. So the bulk of my questions would be focused on that, and I would finish in within 45 minutes, as I said. Is
Okay.
that okay?
Yep.
Okay. As a distinguished physicist yourself and an expert on Einstein to boot, how do you look at a 26-year-old publishing in a span of 8 months 5 seminal papers on photoelectric effect, quantum nature of light, Brownian motion, special relativity, and equivalence between mass and energy?
I mean, it was quite an amazing achievement. It really was a miracle year. These papers, each in its own way, transformed a part of physics that was at the time very much in the works, in the air. Lots of people were thinking about these problems, and each of these papers had an enormous impact. I find, however, that the general public, when they think about this, they think that he sort of came at it instantaneously from nowhere. You're working as a patent clerk. It's like a person working in their garage inventing something that's going to transform everything. But of course, by 1905, he was already an accomplished physicist. He'd published papers. He was corresponding with all the greats in Europe. He was at the patent office because it was a lousy job market when he graduated. And also, he tended to aggravate many of his professors. So I suspect he didn't get great letters of recommendation because he had his own way of thinking. So he was already an accomplished physicist. Still, that doesn't take away from the fact that these 5 papers each was such a marvel that it's really a stupendous thing.
You know, this is beyond inspired. I would call it almost preternatural that someone, forget the age, 26 is a pretty callow age, to come up with some, as you mentioned, each paper transformed some part of physics, and 5 together basically upended physics as we understood. This is extraordinary, isn't that?
Yeah, I mean, I try to explain some of this when I teach. For example, I've taught courses for non-science majors over the years. And try to help them understand what this, for example, the special relativity papers were about. And one thing I tell them that, if you read those original papers and look at the equations, almost every equation had appeared in other papers. He re-derived a lot of things that were already known to Lorentz and Fitzgerald and Poincaré. In some ways, he didn't add much new to the overall mathematics. What he did was change the way we think, and particularly about time. He did something that no one was really willing to do, and that was to think about time as something that clocks measure, not as something that was handed down to us by Newton. And that really freed him to really to get this new picture of space and time together. So, it was an amazing too. He did what no one else dared to do or could think to do. That was just the way he was. And then, of course, he turned to the quantum, and he turned to atomic Brownian motion, and sort of applied the same free thinking that he was used to those problems, and came up with a key new idea. Again, not that much was new in terms of the mathematics, but he taught us a different way of thinking about these problems.
Tell me something. The idea that light is composed of both energy and quantifiable particles, which was what he talked about, was that also in the realm other people were discussing that?
Well, certainly. I mean, Planck had already pointed out that he could get the right black body spectrum if light somehow came in units or packets, of h times the frequency. H is, we now call it Planck's constant, after him, not after Einstein. It was really Planck who came up with this basic idea. But it took him a long time actually to really accept this idea that these things really could be thought of as having a dual nature, wave-like and particle-like. For him, H nu, this packet, was just a feature that helped to get the right answer for the spectrum of the radiation, but he wasn't able to think the way Einstein could think, that maybe there was a kind of duality between these two. And for Einstein, this was still 10 to 15 years before the real development of quantum theory and this idea of the dual nature of materials. But Einstein was able to think it through and really think of the photoelectric effect as, emitting some kind of a blob of energy that might be a particle. I'm not sure his thinking was all that clear yet, but nobody else, Planck included, could actually make that step. To them, it was something that worked, but they didn't know quite why.
But as a physicist yourself, and a distinguished one too, you are the winner of the Einstein Prize as well. Tell me, how do you divine something along on this scale, sitting basically in an armchair and some mathematics? It sounds almost like magic.
Well, it was, but again, he knew Maxwell theory. He knew what Lorentz had done. He was not, as I said, it wasn't, on one hand, it was miraculous, but he was really at the top of his game in terms of his understanding of all the details of physics around him. So he just brought all that prior knowledge together, which he'd studied and learned very well, and brought it together, but used his own intuitive thinking, his way of thinking outside the box, applied to what was then just the conventional laws of physics.
His postulation that light is immutable, constant, and independent of the observer's motion. Tell me a bit about it. How does one arrive at something like that?
Well, in his paper, he does allude, he mentions, although his big 1905 paper had no citations. He didn't cite any literature, which was, by today's standards, would be considered a no-no. He probably should have, but it wasn't his style. But he did say in the paper about, referred, I'm not even sure he mentioned that by name, but he was clearly talking about the Michelson-Morley experiments that had been done in the US in the late 1800s, explicitly looking for the effect of our motion through space because of our orbit around the sun, basically, how that would affect the speed of light. Everyone at that time thought it should affect the speed of light. The light should travel faster if we're moving toward the source and slower for moving away. And then Michael Morley said, well, that should show up in their interferometer, where they bounce light signals back and forth between mirrors oriented at 90 degrees. There should be a signal. And there was no signal. They saw zero. They saw no effect. And I think Einstein was aware of it. He didn't refer to the papers, but that was a key point to him, that in fact, light, from his point of view, had the same speed irrespective of observers. And by the way, that also came out of Lorentz's work on Maxwell's equations. If you take Maxwell's equations and change to a moving observer, the speed that appears in Maxwell's equations for the speed of light doesn't change. Now, again, Lorentz didn't understand this. It didn't make a lot of sense. But Einstein then pulled these ideas together and said, yes, the speed of light is the same to all observers. And here, by understanding how to synchronize clocks, here's how it all works.
You know, it's interesting you should mention, I mean, the way you're describing it, I think you perhaps even use the term derivative. It's not, you don't hear that every day about Einstein, because people are so overwhelmed by his apparent genius that derivative does not figure when people analyze his contribution.
Yeah,
I'm struck by the fact that you're mentioning that. I heard only a couple of other people say that.
Yeah, no, I mean, I've come to the view that, and I'm not a real expert on his life or his history. I, like most people, have read many biographies, but I certainly understand the theory extremely well. And in particular, I've taught it to non-science students and to physics majors. So I think I understand it quite well and understand a lot how he got there. And I really appreciate the fact that, or understand the fact that he really knew a lot already, and he was really trying to tie together stuff that most of the world around him did not understand, and he was trying to make sense of it. But the material was there, waiting for him to bring his new insight to it.
Tell me something. I mean, this is speculative. We are trying to get into his mind. When in 1905, when he came up with these 5 papers in 8 months, would it have struck him that he has perhaps essentially appended physics as we understand?
I think he had some understanding that what he had done was pretty important. I mean, it wasn't long after that, I forget all the dates, where he was about to get divorced from his wife, and he told her that as part of the settlement, he would give her his Nobel Prize money.
Right.
I mean, quite far from that whole issue of his relationship with his wife. I think he understood that he really had been onto something major, and he really had made a huge contribution. And within a year and a half or so, he was asked to write a major review article on special relativity, and it was clear from the letters he was getting back and forth from his colleagues that he had really struck gold.
Right. How do you think he compares with Isaac Newton, whom a lot of people regard as perhaps the greatest physicist of all time? I mean, you're talking about gravity, you're talking about optics, you're talking about calculus. He invented calculus to solve some of the. I mean, it's astonishing that one person could do that. How do you compare the two?
I could only toss a coin. I don't think I'd be hard pressed to choose one over the other, because you have to think in terms of the context of each person's time and period, place in history.
Right.
I mean, obviously, the world of science was much more primitive in Newton's day. In fact, some people even think that Newton really invented science, invented the scientific method, the way of approaching the natural world and comparing that with theory and things like that Newton really originated what we call modern science, on top of the other things. I mean, I don't think Einstein did that, but on the other hand, everything we do in the 20th century traces back to Einstein. So,
that's true. Yeah,
I think they're both just like way up there.
I mean, they're both icons. So
yeah, you can't get away from it.
Another point I'm interested in your view is on the, of course, the famous E equals mc squared, the mass and energy equivalence. It, I mean, I've read this for nearly 45 years now. My background is physics. I have a slim book by Einstein himself. I understand all the words, I understand all the constructs, but somehow the fundamentals frequently elude me. Tell me, E equals mc squared. Isn't that a splendid thing to come up with?
Well, it is, and as I said, I've taught this both
Yeah,
to non-scientists and others. But again, I think it was a product of his way to think of really selecting what's important and what you cannot change, and then what you're willing to change.
right.
So, in relativity, in the first relativity paper, I mean, I think he thought Maxwell's equations were so fantastic, we had to accept that. And then time, well, what's time? Blah blah blah. He's willing to play around with time, which we would think would be, how could you possibly do that? But to him, Maxwell was preeminent, and then other things had to change. Well, in the E equals mc squared paper, uh, to him, the conservation of energy was preeminent, the conservation of momentum. And so when you started thinking about systems that had particles inside moving with also kinetic energy, and how that would look from a moving frame of reference, imposing conservation of momentum in a moving frame of reference forced him to say that the energy in one frame actually looks like mass in another frame, which seems crazy. But he was willing to accept that. But to him, conservation laws were the number one thing. You could not violate the conservation laws. Strangely, when I talk to non-science students about this, when you read his paper, if I translate it into modern vernacular, it was like, guys, you remember that paper I wrote a few months ago? By the way, it just occurred to me, like, duh, what was I thinking? There's another consequence I forgot to put in that paper.
Right.
And there it is. It's like an afterthought.
Indeed,
Yeah.
indeed. What are your views on the quest for a unified theory? I mean, for a universe this unfathomably large and complex, why is it problematic for it to have multiple operating systems, as it were? Why do we need a single theory?
I'm a pretty much not a skeptic, but I have very little enthusiasm for things about unified field theories.
I see.
I mean, uh, there's this claim that we have to quantize gravity.
Right.
Well, I'm open to the possibility that who said that? I mean, why is that so? Why is it necessary that gravity be quantized? We know that everything else is, and everything else wouldn't work if we didn't have a quantum theory. But to say that that implies that we must have a quantum theory of gravity doesn't doesn't impress me all that much. I mean, I understand the
Right.
motivation, but it just doesn't turn me on. Um, and also just unifying the interactions, which is basically the same thing. One of Einstein's problems with his attempts to unify uh, gravity with the other interactions was that he refused to consider the unification from a quantum point of view. And now we understand that's why he ultimately failed. He just couldn't do
Right.
it because we know if you're going to do it, it has to be quantum. My issue is I'm not sure that you really have to do it. But of course, the other thing about a lot of this unifying things like gravity with the other interactions, I mean, unifications within the electroweak and strong interactions has been one of the great successes of
Right.
modern physics, and that's beautiful. The problem with adding gravity to that mix is that um, when you do so, it's extremely difficult to imagine any kind of experiment that would tell you whether you've done it right. The places where a quantum theory of gravity or unification with the other interactions like stringiness and other things, places where these matter are at the Big Bang or before the Big Bang, and if there are multiverses, but we're never going to have an experiment to test that.
Right.
Inside black holes, well, you could test it, but you could never, write a PhD thesis and send it out to submit it. The evaporation of black holes, maybe, although there's not that much there that really involves any grand unification. So and my, even though I'm a theorist, all of my career has been involved with the question of experiment, whether it's
Right.
testing general relativity, detecting gravitational waves, doing gravitational wave astronomy, multi-messenger astronomy. To me, experiment and observation is it. That's what we got to do, even though I'm a pure theorist. So if you can't do an experiment to test these ideas, what do you call it? Is it an actual theory? Is it religion? Is it faith? So again, that's why I don't spend much time thinking about it or working on it. I admire the people who do. Maybe they will come up with something that can be used to test, to distinguish among them. But I don't waste a lot of sleep, worrying about it, because I've got plenty to do just thinking about, observing black holes and
I'm sure,
detecting gravitational waves.
Yeah. This is perhaps a silly question, but I'm going to ask anyway. Is gravity even a force? It looks like a consequence of the way the universe is.
Well, I'm from the John Wheeler Kip Thorne school. I was trained by Kip, and he was my teacher. So I'm a geometry guy.
Okay.
To me, the gravitation from the way we walk around the Earth to the orbits of the planets to gravitational waves to the universe as a whole, gravity is the manifestation of space-time curvature that's generated by mass. You can think of it as a field. It's a more or less an equivalent approach. I feel that the geometrical approach certainly helps one to have better insight into what's going on in black holes and in cosmology than say the Weinberg field theory type approach. But the bottom line is they all give the same predictions. And so there are two different ways, like the Heisenberg and the Schrodinger picture of quantum mechanics. There are two different ways of doing the same thing. One may help you if you want to unify gravity with other things, thinking about gravitons and spins and such. But I think the other is better if you want to think astrophysically and in terms of things like waves.
In your book, Is Einstein Still Right? You write about how scientists have been testing his theories with increasing precision. How long do you think he'll remain right?
I have a joke that I tell.
Sure.
I don't know. I don't know if you're a fan of American baseball, because the joke.
I have a broad understanding, not much.
So you may have. People sometimes ask me, will general relativity ever break down or be modified? And the statement I make is that it would not surprise me if general relativity, as we now understand it, were completely correct all the way down to the Planck scale, where pretty clearly something has to give, right?
Right.
So it wouldn't surprise me if that were true. Now, having said that statement, then I'm immediately reminded of the famous baseball player, Yogi Berra. In fact,
sure.
He's one of my childhood heroes. I've always been a Yankees fan. I met him once, actually.
Oh, I see.
After he retired from baseball, Yogi was asked by his wife, Yogi, you were born in St. Louis, which is where I taught for 31 years. You were born in St. Louis, you played baseball in New York, and you've retired. We now live in New Jersey. If you should die first, where do you want me to bury you? And Yogi said, surprise me. So when you think about the time scale for answering my question, I think that fits with Yogi's attitude.
You also mentioned that general theory of relativity languished for nearly a century before it acquired new respect, sometime around 2015 again. Now we are about a decade from that time. Where are we now? Are people still pushing against it as the ultimate truth?
I mean, the real revival of general relativity occurred in the sort of 1960s and 70s. Turned out it was right around the time I was, joined Kip's group in 1969. So I really caught this wave, this relativistic wave, as it was building up. And I think the main turning point, in my opinion, and again, I'm not a historian of science, but was the detection of the binary pulsar And the report by Joe Taylor that he had discovered the shrinking of the orbit as a consequence of gravitational wave emission. So we sometimes think of that as the first, albeit indirect, detection of gravitational waves. And that, I think, really cemented in people's minds that, general relativity was really here to stay. It was part of the mainstream of physics. And even particle physicists, because soon came the developments of string theory, particle physicists started taking gravity seriously. The whole astro-particle physics connection, using cosmology to learn about particles and vice versa, all of these things were coming along. And in some ways, the 2015 detection of gravitational waves was kind of icing on the cake. But I think the big turning point was Hulse Taylor, and that announcement was 1979.
Right. Did you ever doubt that we would finally be able to prove gravitational waves? Because it took a while.
Well, it took a while, and as I give a talk these days called "The Renaissance of General Relativity," where I talk about the turning point in my career, and I've talked about the fact that in June of 1969, I was just starting to sit in on Kip's group meetings. He'd invite me. I guess impressed him in his GR course, so he invited me to come to meetings. And of course, I didn't have a clue what was going on. Right, I was new. People were at the blackboard talking about what they're working on. Right. I was like, oh, what is this? However, that June, Joe Weber announced that he had detected gravitational waves. Right?
I see.
Using these cylindrical bar detectors. And this is a serious problem because he was seeing signals at several per week, sometimes several per day. He, about a year later, reported evidence that they were coming from the galactic center. But the energy output that was implied by what he was seeing, if he was right, and you had to take him seriously because he was a brilliant experimentalist. He was not crazy. He was, many people think he should have won the Nobel Prize for many things that he did in the past. But no one could understand anything about what could be the possible sources of these waves. So Kip began to worry, well, our calculations of the strength of gravitational waves is based on general relativity. Is Weber telling us that maybe GR is wrong? So he looked around the room, and I think I was hiding behind Richard Price at the time, and he pointed at me, he said, "Clifford Will, this summer I want you to find out everything we know about the experimental validation of general relativity, and because maybe it's wrong and we ought to find out."
Right.
And that really launched my career. Well, Joe Weber and Kip Thorne have launched my career, sort of basically involved in the testing of GR.
Oh, that's fascinating.
So
to change gears a bit, Professor, I'm very keen to know what you think about the origin of the universe. The first debate was the Big Bang versus the steady staters and the Big Bangers, as it were. And the term.
I was at Caltech as a student when Fred Hoyle paid frequent visits. He was a regular visitor there, and he and Narlikar and the big promoters of the steady state theory still.
Yes, in fact, I frequently talked to Dr. Vikramasinghe who was with Fred Hoyle.
Mm-hmm.
Fred Hoyle used as a pejorative term,
Big Bang.
And it became the serious part. So my question is, even someone like Roger Penrose now is saying, talking in terms of conformal, sort of eon after eon after eon, that essentially the universe continues the way it is without any major changes. That seems to be the view. What is your view?
Well, again, these questions all get down to something having to do with just some going beyond pure Einstein. So, there's talks about the multiverse. There's pre-Big Bang models with earlier contractions and expansions, and so again, it's very tough to find a way to distinguish various models of these sorts. I think some of Penrose's ideas have made predictions of circles on the sky, but I don't think the evidence of that is now pretty thin. There's nothing really serious that supports that. Fluctuations of the cosmic background radiation. It's awful tough to see if we could see any kind of signature or imprint of earlier than Big Bang activity. We can barely see the B modes that just talk about the inflation era, which is in some sense long after the Big Bang, in some certain units.
Right.
In Planck units, it's long after the Big Bang. So again, I just don't have a thought about it or an opinion, because to me it's so remote from testability that we may never find out. We may not stop thinking about it, but we may never find out definitively about it.
I see. Another question is somewhat philosophical. I think Steven Weinberg famously said, the more the universe seems comprehensible, the more it also seems pointless. I thought it was quite a remarkable observation. Do you attach purpose or meaning to the universe as a physicist?
No, I mean, my view is it is what it is. It's quite mysterious that it is the way it is, especially if there's only one. Maybe having multiverses is nicer in some ways, because it's like we're not the only story, that there could be other stories going on. But it's really hard from our human perspective, where we see everything in Cartesian space.
Yeah.
Our time is limited to a couple of decades.
Right.
It's really hard to think in terms of the universe as a whole and to make any cognitive sense of it.
Right. But within that frustrating human existence, I'm sure you also ponder over these questions. For instance, I often tell some of my friends, I said, what the hell is Jupiter doing, for instance? What is Jupiter's purpose, or what is the moon do? They are just floating around, orbiting around for billions of years. To what end?
Yeah.
What exactly is going on here? Is it part of some large design that we have no clue about what's going on?
Well, of course, there's also the other point of view, that it's not that there's no real design, but it's just this anthropic viewpoint.
True. No, I understand.
We are what we are because certain conditions allow us to be, and if we weren't here, we wouldn't be observing these things and asking these questions.
Precisely.
And even the moon. I mean, if there weren't tides on the waters in the Earth, maybe certain kinds of living growths might not have evolved in those tidal pools where the water was stagnant for a while. Who knows? But again, I find all these things sort of very interesting, and interesting to think about. To lay people, I try to explain them as best I can. But again, I don't ponder them very deeply myself. I'm not a super religious person, so I don't think in those kinds of terms.
Right.
And at the end of the day, of course, I mean, even if there were zillions of Big Bangs, at the end of the day, our lifetime is limited, no matter what you want to say. And so
Indeed.
The idea is just to do the best we can. For me, learn as much as I can, and maybe hope to pass it on to future generations.
Indeed, no, the same here. Even I'm not even remotely religious by any measure. I've never been. Another point I want to seek your reaction is Einstein never came to terms with the fact about the observer effect in quantum mechanics, that the act of observation brings that world alive.
Yeah.
Otherwise, it's just a fuzzy soup. He was quite frustrated by that. How do you think he would have come to terms with it if he were alive today? Again, that's a speculative question, but I'm interested.
I don't know. I mean, in fact, I've just been reading this month's Physics Today, which has many articles, actually old articles that they published in prior years about quantum electrodynamics, Bell's theorems, plus some more modern articles about entanglement and all the kinds of things that Einstein and EPR railed against. I think today we have a deeper and much more robust understanding of it all and how it works, and of course now we're using it in actual devices and in real world activities. So that's I think an interesting question to speculate. Not the quantum mechanics of 50 years ago, but the quantum mechanics of today.
Right.
If he had a different opinion today than he might have, say, at the time of his death, for instance.
Absolutely, yeah.
Perhaps he might have. Perhaps he might really, especially now that you can really manipulate these entangled states and study them at great distances, where we now understand why the things are the way they are.
Right.
whereas I don't think he fully understood it, but I think we have a much better one. Maybe he could understand that better and be more, comfortable with it.
I mean, he would have been fascinated to see that GPS is a direct
Oh, yeah.
consequence of, right?
Yeah, no, I've actually worked briefly on aspects of that in the
I see.
middle 1980s. Um, there was a period in about 1983 or 4 where the Air Force, which ran the program at that time was a purely military navigation system. There was no thought then of civilian applications. And at that time, I think there were 6 satellites orbiting the Earth. But a small group of relativists had written letters to the Air Force criticizing how they were handling the relativistic corrections.
I see.
And somebody in the Air Force picked up on this and said, well, we better find out, because obviously we want to use this for our troops, so we better make sure we're doing it right. And these seem like experts, and they're telling us we're doing it wrong. So the National Academy, the NRC, asked me to chair a study of the procedures that the Air Force was doing to take the GR effects into account.
Oh, I see. That's fascinating.
So it was about a year-long study, but at our very first meeting, we decided that these relativists, whom I knew all their names and everything, and they weren't crazy, but they were flat wrong, just demonstrably wrong. Their criticisms were based on some somewhat legitimate things. They're relativists. We talk in a certain language. The people who run the program and deal with the actual atomic clocks are engineers. They talk about things and the problem is these relativists had gotten misunderstood a lot of the language that the engineers are using, and thought they were doing things that they weren't doing. It was really a communication problem to a large degree. So we could reassure the Air Force that they were doing everything right. They'd consulted with all the experts, but I love to say that to everybody that when you're trying to find your space in the parking lot outside Target, you're relying on Einstein's theory to navigate yourself around.
Absolutely. To conclude, not since Einstein, or even before that, has there been a singular figure like him, except, of course, Isaac Newton, who has had such a profound impact on science. Why is it that we haven't seen something of this scale in the last 100 years? A figure of that brilliance, all-encompassing brilliance, as it were.
Yeah. I just think it's the growth of the subject. I mean, it's hard to make a contribution of that major scale when the APS has 60,000 members,
right?
And in 12 branches and 8 to 10 divisions and topical groups, and physics is so diverse and so widespread. And I mean, in any given field, there are some giants who've made huge contributions. Obviously, you think of Steven Weinberg and Phil Anderson, and major figures who've transformed a sub-branch of the subject.
Right.
But Einstein transformed almost every branch of the subject, including astronomy. Of course, we haven't even talked about general relativity. I mean, that's a whole other thing. So I think the whole field has grown so much that it's very hard for someone to do something so transformative. And even Stephen Hawking, I mean, he obviously transformed a lot of people's perception of science among the general public. But his contributions were huge in black hole physics. But again, that's black hole physics.
Right.
It's not superconductivity. It's not, it's just a small branch of a very big field.
Yeah, but physics has become so specialized. In fact, it will become even more so. And one bit I was curious about is the rise of AI. Do you think AI might help in terms of the quest for unified theory?
I don't have a strong opinion. I don't follow it very much.
I see.
But I certainly know that people involved, certainly people involved in data analysis are really, when I read in any paper from LIGO, people are talking about, machine learning approaches to such and such, and people analyzing data from Webb Space Telescope, and machine learning and AI is becoming almost an indispensable tool for analyzing huge data sets and trying to glean, information from those data sets.
Right.
How it will affect, and of course, people are now talking about that solving certain kinds of equations with AI much more efficiently than other approaches. In fact, I have to say, I'm just now writing a paper about doing post-Newtonian calculations of gravitational waves and equations of motion. This is for gravitational wave detection in spiraling neutron stars mainly. These calculations are extremely difficult. I mean, you have millions and millions of terms, and we all rely on Mathematica and Maple to do these analytic calculations. But some of when you go to higher and higher orders in this approximation, these calculations become so complex algebraically. It's not numerical. It's just trying to do integrals and get algebraic expressions that maybe you have to think about using AI to AI type knowledge to solve the problems that in a faster way than we can do with the more primitive things like Maple and Mathematica.
Right.
So I'm just writing a paper pointing out some difficulties at these high orders in post-Newtonian theory that perhaps one should think about calling on AI to help out. And I'm making this call because it's not going to be me. I'm old. I'm too old to learn these new fancy
Who
techniques.
knows? You might crack it and live up to another 100 years.
I'd be very happy for some young person to say, "Hey, wait a minute! I think I could to become intrigued by this paper I'm about to write."
Right.
But I say, I don't know what I'm trying to say is this is an important problem, and somebody ought to try to attack it. If I can influence some young person to do it, then I'll feel pretty good.
Hopefully. Indeed, on that note, Professor Will, I want to really thank you for your time. It was a great pleasure to talk to you.